Okay, you might be seeing now my screen, I suppose, and I'm taping. So, good evening, everyone. This is Ashoten, and I'm gonna go over formation of stars, and formation of rocky planets, and formation of planets in general, which is a core subject for the upcoming exam. Just make sure. Okay, you. Oh, Eduard is there too. Hey, Eduard, how are you doing? Good to see you there. Um, so first of all, it's not uncommon when you ask students how stars are formed to hear a description of star formation as being something related to explosion, like kaboom, and then you have stars being formed with an explosion. So a big release of energy and then stars come out. It's interesting also that this sort of a idea existed in the past. There is a group of stars called supernovae and also novae, nova or supernova as one star. So nova are stars that suddenly they bright up. Supernova are stars that suddenly they bright up in a galaxy. So which means galaxy are, as we now know, are complex objects very far away. We have one close, the one we live, which is Milky Way, but in general, galaxies are far away. So when we see a star in a galaxy that is very far away, brighten up, sometimes to the point of matching the brightness of the galaxy with its own display of energy, excuse me, uh, the amount of energy involved is phenomenal, is colossal. And astronomers, ancient astronomers, Greek and Latin astronomer, Roman astronomer, they knew about these objects because they were pretty much observing sky in a very large detail, all different sky regions with plenty of detail. And then in a beautiful night, you have some brightening up star in a given region. So they thought this was a new star being born. That's the name nova, which means new in Latin. A new star is born. Now, today we have a different idea. These new stars being born, these supernova or nova, in fact, are stars, they are dying out. And when they die out, they flash and they release lots of energy. And we will learn this next week when we study stellar evolution, all the steps that lead to stellar evolution and to the last stage in stellar evolution. Now, that goes to the point. So, how stars are formed? How do we call a new star or young star? So, young stars or star formations are processes that require gravity, which is a force that brings material into a point, so gravity. And another important ingredient in star formation is rotation. So gas in the interstellar medium from where stars are formed, so gas is not stationary. So gas is moving. And if you observe the flow of a river, so you don't have all the volume of water moving in one direction altogether all the time. You have globally that motion going on in one direction, but here and there you might find vortex in which some rotation and some motion, independent motion occur. And then you can think the same happens in the interstellar medium where you have giant, as we call giant molecular clouds, GMC, giant molecular clouds, which are cloud of gas several light years in extent, very thin, so very diluted gas. And these clouds, they they orbit the galactic center. They take several years, in fact, several millions of years or hundreds of millions of years to complete one turn. And as they do this rotation, they interact among themselves. And this interaction leads sometimes to star formation. Sometimes these giant molecular clouds are such that as a result of these interactions, certain regions in it get highly dense, which means the concentration of material is high enough to initiate and to seed a process of star formation. So out of this high density region, then gases start to fall in, following gravity forces. So gravity forces, in order to be efficient and form stars, it require a cold gas. So that is the main ingredient of star formation, cold gas. Without cold gas, you can't form stars. Later on, we are going to learn about elliptical galaxies. Elliptical galaxies, on the contrary, with respect to spiral galaxies, they have hot gas on them instead of a cold gas. So hot gas has a tendency to expand, and cold gas has a tendency of being clustered, which means gravity can then efficiently initiate a process of clustering even further, giving rise to star formation. So you gotta have cold gas, and it's so a density value to the gas that allows for the initiation of star formation. And here's a display of what I mean. So you have a giant molecular cloud, and these giant molecular clouds fragmentate itself in different clusters, and then gravity further down on the line of fragmentation bring this gas to a central point, and in the figure it's called center of mass, and then the gas just keep following on there. But remember, I mentioned two ingredients. One was gravity, the other one is rotation. So as the gas falls, it also rotates. And as this rotation occurs, the gas has a preferential direction depending on where the gas is in respect to the center of mass of that system. The gas might prefer to fall to the equatorial region of that rotating gas, and then spiral and slowly fall onto the central star that is being formed. And then we call this central star that is being formed a protostar. So here's the idea. So you have a giant molecular clouds, and you see there is no explosion going on there. So you have a giant molecular clouds, and then you have fragmentation going on with formation of small clusters, and then you have these cores being formed, and out of these cores, stars will come out. But in addition to gravity, you also have rotation. So each one of these cores will be subject to rotation. And this rotating gas eventually collapses to form a circumstellar disk. A circumstellar gas is rotating around the central star. And once this accretion stops, and then the gas of the remaining gas in the circumstellar disk will give rise to the host of planets and satellites and asteroids and comets that we know are part of any solar system. So we saw in previous chapters that now it is found that any star in our galaxy has, without statistically speaking, has a planetary system, at least 2 planets in each of the stars that you observe up in the sky. The question is, which one of these stars might harbor life? So again, 20 or 30 years ago, you would think that stars were kind of an isolated system. We suspect there was planets, There was asteroids and comets in them. But now we know they are there because we have observed using these two different techniques, Doppler effect, which has an effect in wobbling the star so that you can measure Doppler effect on the star, but also the transit method that produce a dimming of the starlight, and then you can assess information about the planets by studying the fraction of this dimming light. So as these circumstellar disks start to collapse and flatten even further, eventually you form a protostar in the center of that cloud. Now, there are several regions of star formation in our galaxy, and they have been observed primarily in the infrared. So infrared is a light that has the property of being able to transpass gas without too much impedance, as opposed to optical light that is easily subtracted from the light beam. For instance, optical light, the one we can see with our eyes, and in general, ground-based telescopes like the one we have in our observatory, these telescopes are good to observe optical light, but optical light in its terms, they do not travel easily through the interstellar medium because dust that exists in the interstellar medium easily subtracted this light out of their beam. But infrared light can go through the interstellar dust and without too much scattering. So astronomers can build infrared detector that allows them to see these regions of star formation. And here's one of the final stages. Let me show you. There is a nice video, and I think I showed it before. EX Lupi. So this gives you an idea of star formation and the interaction of the
fading light of a flaring young star.
And the interaction of the star magnetic field with the circumstellar disk. But pretty much that's it. And I think some of the animations or videos that I allow you to watch and be part of the discussion show exactly this phenomenon. Let me advance here. There you go. This is just one of these Freeman sequence stars. So you have the protostar in the very center, you have the accretion disk, and then eventually the gas of the disk falls onto the star, guided in fact, but you don't need to know these details, but guided in fact by magnetic field lines the star itself produces. And the star, these young stars, they tend to be very active to the point that sometimes they undergo flares, they undergo all kind of changes, and these flaring moments affect and change the chemistry and the characteristics of the circumstellar disk. So this is a video based on EX Lupi. They found using infrared data, they found a mineral named olivine in the circumstellar material of the star, and they are proposing this olivine, these green minerals, is being formed as a result of flaring of this star when the gas in the disk falls on it. It's a nice theory. It's a very good theory, and is primarily supported by the ideas we have on star formation. But basically, that's how stars are formed. you've got to have cold gas, and cold gas implies the existence of dust, and then you have to allow gravity to take that gas over, and then cluster and bring that gas to a center of mass where a protostar will be residing. And as the gas falls, it doesn't fall raining directly to the center of mass. In fact, it falls towards the circumstellar disk, and then out of the circumstellar disk, it rotates and spirals onto the star. And then eventually, out of this remaining gas in the circumstellar disk, planets and satellites and other solar system objects will be formed. Now, as this protostar keeps evolving and receiving more gas, gravity slowly but surely compresses the star. So a young star in that phase is called pre-main sequence star. Is huge, is like a giant star, 10 times bigger than the sun itself. But because of gravity, so gravity keeps bringing the gas and compressing the gas further down in a line to the point that eventually in the core of the star, the temperature will reach a value where fusion reactions can take place. So when fusion reactions, think about nuclear reactions that we have in power plants. So it's not that. So fusion reactions is a reaction by which atoms of hydrogen, which are very light atoms, they are fused together producing helium atoms, and as a result of these fusion reactions, energy is released. Gamma rays is produced, and gamma rays are energy, as we studied in chapter 4. So when this energy is produced, it migrates, it comes out of this core of the star, and then migrates and propagates out to the external regions. And now the star reaches a phase in its life in which the center part is releasing and producing energy and releasing, and that energy is able to overcome the gravity contraction. The star reaches a point in which contraction is balanced out by this attempted to expand as a result of energy that is produced in the core. When the star reaches that phase, we say that the star is in hydrostatic equilibrium. There is an equilibrium between the force that brings the star to a contraction and the outward forces that tend to expand the star. When these two forces balance out like a tug war, the star remains stable in its diameter, in its size. It doesn't expand, it doesn't contract, it doesn't heat up, and it doesn't cool down. It remains more or less with an average temperature for a long time. And since these fusion reactions that is happening in the core, it happens for a long time, and the hydrogen content in the stellar core is significantly large, the star keeps producing and releasing this energy most of its lifetime. So when the star becomes what we call a main sequence, when the star reaches that phase, the star is called stable. And the star is called a star. It's a stable star. It's a main sequence star. The sun is a main sequence star. The sun is burning hydrogen and convert hydrogen in the core into helium, as it said in this label here. Now, if the protostar, if the center star is less than 800th of a solar mass, which means is about 100 less massive than the sun will never, or that star will never be able to initiate fusion reactions. Will be what we call a brown dwarf or become a planet. So if the star is not too massive, President Jupiter Jupiter is not a star because it was not massive enough to initiate this fusion reaction cycle in its very core. So here are images of these young stars. You can see in this image the black line that goes across the disk represents or indicates the presence of a circumstellar disk. So we are primarily looking at the system edge on. And what we observe in these young stars as a result of conservation of angular momentum, as astronomers say, these stars develop this bipolar flow, this flow of gas in two directions. So bipolar flow, you can see here, you can see there. And the effect of producing a rotating star is the Ballerina effect. So we have a conservation, and using a technical term, it's a conservation of angular momentum. So the more contraction the system has, the faster its angular velocity is, so that you can conserve that amount of rotational energy or property the gas itself has. More indication here of a bipolar flow and the accretion disk. Here again, you can see the circumstellar disk kind of in blackish, and the bipolar flow perpendicular to it. Now, once these disks are formed in that animation, the animation I just showed you of EX Lupi indicate, so eventually the gas in the disk will drop to values where crystallization can occur. You have what is a process by which gas becomes solid. Gas creates crystals or particles, solid particles. Now, there are two things you have to consider where these crystals are being formed. If they are being formed closer to the sun, since the temperature is high, the crystals that will be able to be formed are crystals that can be formed in an environment that is hot, hotter than 1100 Celsius, hotter than 1700 Celsius. It's very hot. Whereas if you are probing regions in the circumstellar disk that are further out, the outskirts of the circumstellar disk, now the temperature in these regions are very low, which means you go down from a temperature scale that allows you to form dust, like rocky dust or metal dust, but also go down to a value in temperature that allows the disk itself to form ices out of volatile type of gases. So you can have methane forming gas, you have carbon dioxide forming gas, and water forming ices, because these regions are of a low temperature enough to allow for ices formation and crystals formations of rocky material. So because of the central star is a hot star, the circumstellar disk that forms around the star will, as it evolves, it will form solid material of two different categories. The solid material that is formed closer to the star, it is going to be more of a metal type or metal oxide type or a rocky type. Whereas material that are crystallized further out in the disk will be those, because it goes from high temperature to low temperature, so it's going to form the metal oxides and so on, so on, so on, but also form volatiles. In other words, out of this little dust, and as time goes by, this little dust, they stick together in the same way that snowflakes stick together when they fall. and they form these nice crystals with an hexagon shape. So the crystals that are formed next to the sun will stick together in a process astronomers call accretion and form bigger materials, bigger rocks, and these rocks are called planetesimals. Planetesimals, here's the word planetesimals, these are important. And these planetesimals just keep on growing because as more of those flakes stick to them, they grow in bigger size. And eventually they grow to such a huge size, they can be called even protoplanets. And because they have enough mass, enough weight, they can start attract material to them using gravity forces instead of electrostatic forces, like sticking together like snowflakes. So gravity of these huge planetesimals start to attract material onto them, and then we call them protoplanets. Protoplanets. Now, if you are probing material or planetesimals that are formed further out in the disk, these planetesimals include on them not only these rocky or metal oxide type of materials or crystals, but also ices. So we have a combination of both. Which leads to, as we study in the book, the two types of materials that are formed. You have the so-called terrestrial type of objects like Mercury, Venus, the planet Earth we live, and Mars, and their moons. So Mars has two moons, Phobos and Deimos. Earth has a moon, we call moon, which is relatively large. They are rocky type of objects. And you have also the asteroid belt, which is a rock type of object. Probably the asteroid belt is comprised of objects that never grew and stick together to form a smaller object, like a smaller moon or a smaller Mercury in that region, because some astronomers suggest that Jupiter's gravitational field prevent that from happening. Now, if you go to the regions further out, now you have these huge giant planets that as they accrete material that abunds in that region, they grow in size, but they are primarily formed with hydrogen and helium. So that's what they are primarily made of. And if you look at the structure of Jupiter and Saturn, they are more of a gas or liquid giants. So if you go to their interior part, they are more made of liquid hydrogen. And if you go to the external regions, they are more of a gas type. Now, and if you probe Uranus and Neptune, those are more of ice types, in response to their density and temperature, interior temperature, and the type of material they are primarily made of. And this diagram here indicates exactly what I just said. Here is the central star, or the protoplanet, or the protostar, where the protostar is formed. And as you move away from that star out to the external regions of the accretion disk where the temperature drops, you have a completely different set of material or solid material formation. You have highly volatile materials in the regions beyond the Saturn regions. You have water ice formed in regions beyond Jupiter, and you have all kinds of refractory materials, which is pretty much silicates and carbonates, formed all over the disk. So when you put them together in what we call a planet, so planets that are formed further out, they will be primarily volatile materials and also refractory materials and water ice. But if you go closer to the sun, you're not going to have abundance of water ice or volatile materials because they will be taken out. But yet you're going to have refractory materials primarily. Now, how? Just a second. How do you probe the atmosphere of these planets? So they have a primary atmosphere. What is the so-called primary atmosphere of these planets? So when the planets formed, and now you have planets being formed, the atmosphere, the first one they had, is called primary, probably was made of the gas that exists in the disk, hydrogen and helium. So this rock, in the case of terrestrial objects, um, simulations and the calculations indicate that a rocky central planet was formed surrounded by a thin layer of hydrogen and helium, because that was the gas abundant in the circumstellar disk, which is the primary gas abundant in the sun itself. But eventually, these light elements were not able to be retained by the planets itself because they are too light. The gravitational force is not able to retain them, first. And second, the sun's radiation and the sun heat is able to scrape them out and to sweep them away out to regions away from the sun. Now, then you have a secondary atmosphere formed, which is not the original one. So the secondary atmosphere came to be formed once these terrestrial planets, and that goes to the chapter 6 that we go in terrestrial objects. Once these terrestrial planets, think about Mercury, Venus, our planet Earth, initially they were completely melted, right? Because they were where is the heat of a planet comes from? Well, it comes from these collisions that help them to be formed. So we have gravity, slowly contraction the object, and then you have a conversion, as astronomer says, of gravitational energy into thermal energy. So the central part of the planet is hotter than the surface. So we are talking about 9,000 Fahrenheit just in the core. So this is happening, but the surface eventually becomes crystallized, becomes solid. And then you have a circular or a spherical planet with a crust that is hard because it has been hardened, has been crystallized. But as the temperature drops, now this internal energy must be released in all kind of volcanic activity. And volcanoes are well known for releasing carbon dioxide, vapor, and nitrogen, sulfur. So eventually we have an atmosphere that is primarily outgassing, that is primarily spilled out by volcanic activity. So that's the atmosphere we ended up with. So that's the secondary atmosphere. And once we study the evolution of atmosphere on Earth and the fact that eventually life kicked in on Earth. So once life kicked in on Earth, cyanobacteria, the first anaerobic type of microorganism that we have evolved on Earth, they release oxygen as a result of their chemical internal energy exchanged with the environment. And once oxygen were released in the atmosphere, now we have a whole generation of rocks being oxidized by this oxygen, and eventually we have an atmosphere that has some percentage of oxygen, which we require to be alive. So our atmosphere on Earth is primarily nitrogen, with a small percentage, 20%, 21% of oxygen. It's 78 parts of nitrogen and the remaining of oxygen. And if you look at Mercury has no atmosphere because it's too small to retain one, and Venus has an atmosphere that's 100 times denser than our own atmosphere. but it's an atmosphere of carbon dioxide. And then if you go to Mars, Mars has an atmosphere that is 100 times thinner than our atmosphere, is also primarily made of carbon dioxide. So Mars is losing its atmosphere because it's a smaller planet, and gravity in there is not able to retain it, to keep it closer to the planet. So we talk about these different methods of detecting exoplanets. That is the Doppler effect method. That Doppler effect is the effect that allows highway patrol to give us tickets if we go above certain limits. So they send a signal to the car that bounces back to their receiver, and by comparing the frequency left to the frequency with the frequency received, you can determine with very high precision the speed of the car. So there is no debate there. So stars are not reflecting light that we send from Earth, but the stars are sending light. So when the stars moving towards us, we see their original transitions, their original lines or color, to be slightly changed to the blue. And when they move away, they slightly change to the red. And we call this effect the Doppler effect. But the main point is we can use these measurements, which is very much easy to be made using current technology, to determine the distribution of velocity and motion of stars in the sky. And this method was used to determine the first exoplanet around stars. And these exoplanets ended up being giant or Jupiter-sized planets that were exerting a torque or a pull in the star, and the star would circle and rotate around a common center of rotation. Let's see if I can. I think we have, if you go to, so let's run the animation. So this is a star and a planet that goes around this star, and they have a telescope, right? So this planet here is supposed to be a Jupiter-sized planet. Of course, it's not in scale, but just think about the planet itself and the star. They are both orbiting a common center of mass. So the star wobbles. And with a telescope, as you can see in the spectrometer, you can pick that motion. See that? So sometimes these traditional lines that you know where they should fall moves to the green part of the spectrum, and then to how much they move, you can detect the motion of the star itself and infer the property of the planets responsible for this pull. And then you can associate that with a planet, with the existence of an exoplanet. So that is the Doppler method. That's the Doppler shift. Another one is the transit method, when the planet crosses the star, and as you can see in this diagram here, it causes a dimming on the planet light curve. And then you can use not only the size of this transit, but also the depth to infer the ratio between the size of the star and the size of the planet. And then you have direct image of stars, which is more difficult to be made, or direct image of the planets, which is more difficult to be made, but it is going to be one of the important methods for planet imaging once you are able to eliminate the brightness of the central star. This is a node. This is a node um, diagram. In fact, most of the planets found are in this category here, Neptune size. But once you correct this found information for biases, in fact, most of the planets found around the star, they are in this category here, Earth size, rather than this size. Okay. And pretty much that's it. Let me go back. Who is this guy? Okay. Well, what about that? And pretty much that's it. Hey, Hiani. Good to see you. So, any question? So that is the main point of star formation. So we have a video that you have to work on. Renee got some extension, but it is about the moon's formation. What are the theories behind the moon's formation? And then you have to watch the video. It's not a long video. It's pretty cool, and it has nice animations. Okay. We have a midterm coming up this week, and it's gonna be open on Wednesday night, and then you can try on Thursday, and then you have a second and last attempt on Saturday. Okie doke. All right. Okay, any question? Let me stop taping now. Good night to all of you.